Yeah, it's like so. I was kind of flip, and I told Katie that her pretty please wasn't going to work, and we're going to have a quiz before Thanksgiving. We don't actually have to have a quiz on the Tuesday before Thanksgiving break if you don't want to. Um, we will have had, we've had 19 quizzes. We'll have two more, so it'll be 21 quizzes at the end of next week. What I'm planning on doing is, however many quizzes we have, I keep the top 15. So if we have a quiz the day before Thanksgiving, you will have had 22 quizzes, and I'll drop 7 and keep the top 15. If we don't have a quiz the Tuesday before Thanksgiving, we'll just drop one less. I'll take the top 15 out of 21 quizzes instead, so drop 6. Um, so the two reasons I think you might want to have a quiz the Tuesday before Thanksgiving: one, I drop one more quiz if we do that, so that gives you a chance to recover from a quiz score from the past that you don't really like. And two is, if we don't have a quiz, there'll be quite a few reactions that you won't have been quizzed on at all. So the first time you'll see them is on the exam, and sometimes that reduces the exam score because you don't have a chance to get it wrong on the quiz and then figure it out and change your understanding so you get it right on the exam. I'm definitely not going to have a quiz the Tuesday after Thanksgiving. I think you're going to have a lot of stuff due that week, and we have an exam on Thursday, and you don't need another quiz in the week after Thanksgiving break. I suspect that week is going to suck, especially since all your other classes that haven't been remote will suddenly have to be remote for a week, and maybe they won't adjust very well. So it's kind of up to you. If the class consensus is that you don't want another quiz and we'll just have 21 quizzes and drop 6, I'm willing to go with that. You don't have to decide now. We can decide that next week. But anyway, that's the option. Oh, I didn't mean to be recording that, but I guess I was recording that discussion. Oh well. So anyway, if we do have a quiz, it'll be another kind of reactions mechanism quiz. Next Tuesday will definitely be reactions. Next Thursday will definitely be mechanisms. And then the following one, yeah, what the heck, right? If you get a 0 on it, then you just drop that one. It's no big deal. Anyway, so the other thing that I wanted to talk a little bit about today is preparation of alkenyl halides. And these are in videos that you haven't watched yet. But it's a halogen, like a bromine, that's on a carbon-carbon bond. So something like that, right? You can't put a hydroxide on a carbon-carbon bond. That's called an enol, and enols are unstable. But you can put a halogen on a carbon-carbon double bond, but you can't do it by free radical halogenation. Because the sp2ch bond is too strong. Right? And if the sp2ch bond is stronger than the hydrogen halogen bond, then that reaction is going to be very endothermic if you try to pluck that hydrogen off with the bromine radical, right? And we know this sp2ch bond is going to be too strong for that. So the only way you can make alkenyl halides is either from a dibromide, right? If you have a vicinal dibromide, it looks like that. And it's vicinal because the two bromines are on adjacent carbons. Or you can make it from an alkyne. Oops, drop the CH2 group. So if I'm going to make it from the vicinal dibromide, what kind of reaction is it? Let's write out the whole reaction. All right, so we've got these two bromines, 1,2-dibromobutane, and I'm going to try to make from that one bromo, one butene, and in this case I've written it as the E isomer. What type of reaction is that? Substitution, elimination, addition. That shouldn't be a hard question, but if
elimination.
It is elimination. Sorry, I didn't see Katie's comment because I'm actually looking at the movie screen. So this is an elimination reaction. What kind of elimination conditions are we going to want for a dehydrohalogenation? Is that going to be E2 or E1?
E2?
Yep, E2. So we're going to want to do this by E2 elimination. Right? Dehydrohalogenation is generally done by E2, strong base. Dehydration of an alcohol is generally done by acid catalyzed dehydration, and that's E1 elimination. So this is going to be E2, and the hydrogen I want to remove is this one. So what kind of base am I going to need to remove that hydrogen as opposed to this one? So we can start thinking about the mechanism, right? I'm going to be taking this bromide off, and I'm going to be taking this hydrogen off. What are the stereochemical requirements? Oops, that's bromine.
They have to be anti-periplanar.
Yep. And if I want to remove this hydrogen, which is the one that's on the sterically less hindered end, as opposed to this hydrogen on the sterically more hindered end, what kind of base do I need?
Sterically hindered base?
I need a sterically hindered base, a strong sterically hindered base. It needs to be a good enough base to take off a sp3 carbon-hydrogen bond. So what would be a suitable choice?
Yeah.
LDA would be probably the best option. Lithium diisopropylamide. So then that's going to do an E2 elimination, and because it's sterically hindered, it's going to want to take the more accessible hydrogen. So that's not really a new reaction. Right. Concerted transition state. And it's going to arrange itself in such a way to try to maximize the separation of the bromine and the ethyl group in the product, which is why we're going to get primarily this E alkene. What if you wanted the other one? What if we wanted to make this one instead? From the same.
We use a base that's, or a strong base that's not sterically hindered.
Yep. Oops. Ah. We're on the wrong ship. So in this case, we want to take off the hydrogen that's over here. So we want to use a non-sterically hindered base, maybe methoxide ion, to generate the more substituted bromide. Both of these are di-substituted double bonds, right? But this one's di-substituted both on the same end, so geminal versus vicinal. What happens if I use excess methoxide?
Will it make an alkyne?
It will. Right? There's no reason why I couldn't take this hydrogen off. So we can do a double dehydrohalogenation to make in this case, a terminal alkyne. We'd make 1-butyne out of it. It is not always possible with these weaker bases like methoxide ion to stop at the alkenyl halide. Sometimes the terminal alkyne is the product that you get. Usually with LDA, because you're running that at low temperature, LDA reactions are generally run at -78 in dry ice and acetone. It's usually possible to stop at this terminal bromide. So that's one possible way to do it. The other possible way is from the alkyne. What kind of time am I looking at? Oh, we got time. And if we're going to turn that alkyne into the corresponding alkenyl bromide, what type of reaction is this one? You want to go 2 for 2, Katie?
I think it's addition.
Definitely. Hydrogen and the bromine that we've added on the same side would not have gone 2 for 2. Well, good thing Isabel broke in there then. But the catch is the bromine here is on the less substituted end. And that's what we call an anti-Markovnikov addition. And that has to be done by a free radical mechanism. So what we need to do is generate bromine radical. This is now an electrophile. So that electrophile is going to get attacked by the carbon-carbon triple bond. So we got our bromine radical here. It's electron deficient. The carbon-carbon triple bond is going to attack that. And it's going to generate the more stable radical. It's going to want to put that radical over here so it can be stabilized by hyperconjugation. And you'll see that that's a general truth. The electrophile always ends up at the less substituted end so that you can put the radical or the cation, if it's a carbocation intermediate, where it's most able to be stabilized by hyperconjugation. So the bromine radical adds to this end, and then hydrogen bromide will transfer a hydrogen. So propagation step 2 is going to be a proton transfer, not a proton, sorry, a hydrogen radical transfer, breaking the HBr bond and regenerating the bromine radical. So this is propagation step 2. is propagation step 1. If I put those side by side, you can see the whole mechanism. Right. So we generate a bromine radical, we add the bromine radical to the CC triple bond to make this more stabilized kind of secondary radical, and then we react with HBr. So the overall reaction looks like this. It's the sum of the two propagation steps. Yeah, I could get it right. It would help. And the only difficulty is figuring out how you're going to generate that bromine radical in the first place. And that's done with peroxides. So you take a peroxide like ditert-butyl peroxide, and react that with HBr and heat it up. This bond breaks because it's very weak. The bond dissociation energy of that peroxide is only around 39 kilocalories per mole. So heat breaks that up, and then it pulls off a hydrogen to generate the alcohol and the bromine radical. And that's a very strong bond, much stronger than the HBr bond, right? So because of the size of bromine, so that's a favorable reaction. So this is called the peroxide effect. In the presence of peroxides, HBr adds anti-Markovnikov, and in the absence of peroxides, it adds the other way. Giving the more substituted bromide. And that's because this one has carbocation intermediate. So that's where I'm going to stop. Do the terms anti-Markovnikov and Markovnikov make sense? Have you seen those yet? I think not, right? Because those are not in the first 3 videos. Those are in videos 4 and 5. When I say Markovnikov, what I'm saying is that the large atom, in this case the bromine, ends up at the more substituted carbon. And when I say anti-Markovnikov, the large atom, right, the bromine, ends up at the less substituted carbon. It turns out that this reaction I just showed you only works for HBr. It doesn't work for HCl or HI. And a later video that you're going to watch will make it clear why that's true. All right, I've got 13 minutes left. If anyone has any questions, you are welcome to ask them.